So hello everyone, I'm Minsun Kim, and today I'm going to present our work Adaptive Online Learning for Text Classification under Distribution Shifts. And our code and data are available on our GitHub page. So the most accurate approach to continuously streaming data is retraining the entire model with accumulated data, which is known as offline learning. However, this is often infeasible in the real-world online learning environment due to the enormous update overhead, uh, especially in the neural network-based model. So, online learning has been proposed as an alternative, which involves updating the model sequentially with the streaming data for their efficient adaptation. And especially these online learning techniques has been become important in the problem of text classification due to their inherent uh, word word uh, word context and inherent shift in the word context and learned representation. So the previous online learning techniques can be categorized into two different category. And first is the accuracy-oriented approach. And this approach focuses on maintaining a high level of accuracy, but they are often limited in their ability to adapt the model in real time. And in real-world online learning scenarios, even the highly accurate model that fail to meet the required learning time uh, can be rendered as impractical, so efficiency-oriented approaches has been proposed. These focus on their fast adaptation to the streaming data. However, they are limited in their accuracy. So in our approach, we devise a we propose a novel module-based update approach, which find a balance between the both aspects, which is efficiency and accuracy. And this approach focus on updating the model selectively based on the distribution shifts and dynamically adjusting the degree of model update uh, according to the preference between the efficiency and accuracy. And our method proactively measure the distribution shift between the two consecutive time points. And based on this measured distribution shift, we find an optimal update strategy to update the model and update the online learning model using those optimal update strategy. And the core of our problem is how to find this optimal update strategy regarding the trade-off between the accuracy and learning efficiency, considering how the extent of distribution shift affects the degree of accuracy degradation. So in this problem, in our modular update approach, we decompose the entire text classification model into four distinct modules with each distinct roles. So these are tokenizer, word embedding, and feature extractor and classifier. And this modular design accommodates a uh, broad comprehensive neural network-based models. And to update this model in a real-world online learning scenarios, there is a need to develop a countermeasure to efficiently and effectively measure the degree of distribution shift in the real time. So to achieve this, we propose three novel indicators to indicate this, which are frequency indicator, semantic indicator, and vocabulary indicator. And each of these modules has been uh, developed as focusing on the corresponding module, specifically frequency indicator for the tokenizer, semantic indicator for the word embedding, and vocabulary indicator for the feature extractor. And consequently, a decrease in this each indicator signifies a shift to a new data distribution from the perspective of each module. And as this decrease directly impacts the accuracy degradation, uh, it means that this frequency indicator can play a pivotal role in guiding the time point for each module's update. So in our approach is composed of two primary paces, which are offline pre-training pace and online update pace. In offline pre-training pace, we first train the two different models, which are online classifier and accuracy predictor. Online classifier is a main classification model, which recalls a continuous adaptation to the new data. And this accuracy predictor, which predicts the accuracy improvement of the model, it accepts the necessity of updating the online classifier based on the measured distribution shifts. So for this accuracy predictor, we use a non-parametric machine learning based models, such as k-nearest neighbor, decision tree, and random forest. And during this offline pre-training phase, we first extract the mini batches uh, to cover the broad spectrum of distribution shift. And by using those batches, we calculate the distribution shift indicators and measure the accuracy improvement and learning time for each effective update strategy. Here, we define the effective update strategy as strategies that with advantages in accuracy improvement over learning time when updating the online classifier for every update strategy. And by using this measured accuracy improvement and learning time and distribution shift indicators, we train the time predictor and accuracy predictor. So these two models are used in the online learning phase to uh to 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 assess the degree of distribution shift without evaluating the entire model. In the online update phase, distribution shift indicators are calculated from the real-time data stream, and these measurements are fed into the two pre-trained models, time predictor and accuracy predictor. By using the pre-trained time predictor, we estimate the learning time with each update strategy, and by using the pre-trained accuracy predictor, we estimate the accuracy improvement achievable with each effective update strategy. And by using those measured time and accuracy, we calculate the effectiveness update score using the preference weight lambda. Here, the preference weight lambda is from 0 to 1, has a value from 0 to 1, and we and consequently we define the optimal update strategy which maximizes this effectiveness update score. And finally, we update the online classifier using this optimal update strategy. And in the experiment, we employ the 5 real-world data sets spanning 3 different domains. So for the experiment, we construct the real-time streaming batches for each domain as follows. In the cybersecurity domain, we use first three batches from the pre-training dataset and the following 5 batches from the different data origin. And in disaster domain, we use the first 4 batches from the different data origin and the last batch from the pre-training datasets. The first table shows the performance comparison between the static update strategies and our method. And according to the result, our method with lambda of 0.9 shows higher accuracy than full model updates with less learning time. And also with our method with lambda of 0.5, we can reduce the time by 36.72% compared to the TFC strategy while maintaining a similar level of accuracy. And in the second table, we compare our method with the static update strategies on different base models. The results shows that our method outperforms the static update strategy, both LSTM and transformer-based models, and also it shows a higher accuracy with less learning time at the range of lambda equal to 0 to 7 to 0 to 9. And also, it is interesting to find that when we adjust the lambda more preferable to the learning efficiency, we can we can reduce the learning time while maintaining a similar level of accuracy. And also, the next table compares our method with the existing method. And according to the result, we can find that our method can be adjusted and flexibly adjusted to beat the performance of existing models uh, in both aspects of learning efficiency and accuracy. And the last table compares our method with the large language based method. And the result shows that our method shows less accuracy than a large language based model. However, these large language based models are not suitable for the real world online learning scenarios, which are dealt with in our study, for because they are limited in their ability to real time adapt the model in the real time. So in summary, our method is the first research effort to find a balance between the learning efficiency and accuracy for the problem of online text classification. And for this, we devise novel distribution shift indicators to uh, to find the optimal update strategy without the entire model evaluation. And throughout the extensive experiments, we show the effectiveness and feasibility of our method in the problem of the online text classification.